Everyone, I'm Jayashree. Today I'll be presenting our work Synergy, a system that looks beyond GPUs for DNN scheduling on multi-tenant clusters. This is joint work with Amar and Jana from Microsoft Research and Vijay from UT Austin. With the growing popularity and scale of deep learning, enterprises and cloud data centers manage large GPU clusters on which several users can request to run their DNN training job. Such multi-tenant GPU clusters typically run a variety of training jobs across different domains ranging from image, speech, and language models. So to manage the large number of incoming jobs, there is a cluster scheduler that uses a scheduling policy like FIFO, SRTF, or LAS in order to optimize for a cluster metric like the job completion time or make span. And this scheduler is responsible for allocating appropriate resources and running the DNN jobs on the available servers in the cluster. Now, an incoming DNN job in such a cluster specifies the number and type of GPU resource it requires to run. And in addition to these GPUs, these DNN training jobs also require auxiliary resources like the CPU cores and DRAM in order to perform pre-processing operations. DNN schedulers today allocate these auxiliary resources to a job in a GPU proportional manner. So what I mean is, say for instance, there's a server with 4 GPUs. And if a job now requests 2 GPUs, which is 50% of the GPU capacity, then proportionately 50% of memory and CPU cores are allocated to this job. But such a GPU proportional allocation is not really the best we can do. And we find that different DNNs exhibit different levels of sensitivity to the amount of auxiliary resources that are allocated to them. Now, for example, let's consider CPU sensitivity. Here I'm plotting the epoch time of 13 different DNN jobs against the number of CPU cores that are allocated to them on a V100 GPU. And here the GPU proportional share is about 3 CPU cores, which is the CPU to GPU ratio on ML optimized servers like the DGX2. On the left, you see jobs that are sensitive to CPU allocation because they perform heavy pre-processing. So as you increase the number of CPUs that are allocated to them, their epoch time reduces. But for the models on the right, CPU allocation really doesn't matter much. They are insensitive to the number of CPU cores that are allocated to them. In fact, if you give them lower than the default GPU proportional share, their throughput is unaffected. So our work is motivated by the key observation that different workloads have varying CPU and memory requirements. And this leads us to the central idea of our work that we can improve cluster-wide performance by performing workload-aware allocation of auxiliary resources rather than the default GPU proportional allocation. While the idea is hopefully intuitive, imparting such resource sensitivity raises 2 important problems which prior work haven't tackled. So the first is to identify what is the ideal resource requirement for each job. And the second is to find out how to pack these jobs onto the cluster in such a way that the overall cluster throughput improves, especially given that these auxiliary resource requirements are tunable. So to address these challenges, we introduce Synergy. Synergy is a resource sensitivity aware scheduler for DNN training. So Synergy first identifies each job's best case CPU and memory requirements using an optimistic profiling technique. It then augments a heuristic resource allocation mechanism to any chosen scheduling policy that the cluster uses, and it performs multi-dimensional resource allocation. So using these techniques, Synergy is able to improve the overall cluster metrics, like the average job completion time, by up to 3.4 times compared to the traditional GPU proportional allocation for the same scheduling policy. So in the rest of this talk, I'll talk about the design of Synergy and present some evaluation numbers. So the overall design of Synergy is as follows, right? Job requests in the incoming job queue are first profiled offline by Synergy's profiler in order to identify their resource sensitivity. And this sensitivity profile is now attached to the job, and these jobs are placed in the wait queue. Scheduling happens in rounds of fixed time duration. And in each round, Synergy's placement module will identify the next set of jobs to run, their resource allocations, and their placement decisions in order to create an execution plan for that round. And it deploys these decisions onto the cluster. So the two primary components in Synergy is profiling and placement. So we'll talk about both of these aspects in a bit more detail. Profiling in Synergy happens in an offline fashion. So in the profiling phase, we want to measure the sensitivity of the job to its CPU and memory requirements, and basically fill up a matrix of this sort here, where we record the job's performance for different combinations of CPU and memory. But as you can guess, to fill up each data point in this matrix, we need to run the job for a few iterations. And this can quickly become prohibitive in terms of profiling time. So in order to make profiling feasible, what Synergy does is that it profiles only one row of this matrix. That is the CPU sensitivity when the data set is fully cached. And all other data points here can be analytically estimated by modeling the network behavior using just the metadata of the data set, the memory and storage bandwidth, and the cache size. And the main insight that enables us to use such an optimistic profiling technique is the repetitive and predictable nature of DNN training, as well as the use of DNN specialized caching like MinIO, which results in predictable cache performance. And to further reduce the profiling overhead, we discretize the CPU space and profile limited points that are sufficient to reproduce the performance trend. So more details on the algorithm for discretization is in the paper. So once the job profile is obtained, the matrix would look something like this here, right? So deeper the shade, higher the performance of the job. And the least value of CPU and memory that gives the best performance is chosen as the job's ideal resource demands. And this profile is then attached to the job that goes on to the waiting queue. Now, moving on to the next module in Synergy, which is the job placement. That is allocating auxiliary resources and packing the outstanding jobs onto servers in the cluster. So the way Synergy tackles this is we first formulate a theoretical upper bound on the optimal throughput that's achievable in the cluster. So we formulate this as a two-stage LP problem. The first LP assumes that all the resources in the cluster are available in one super machine, and it identifies the resource allocation per job that maximizes the cluster throughput. And in a second LP, we decide how to place these jobs across physical servers while minimizing the number of fragmented jobs. Now, although this provides a theoretical upper bound on the cluster throughput, there are two main challenges here. So the first one is that solving two LPs per scheduling round is computationally expensive. And second, it's operationally challenging to implement these scheduling decisions because it can result in fractional GPU allocations. So Synergy introduces a new heuristic tuning mechanism for job placements that we empirically demonstrate to be close to the optimal throughput. So this is how Synergy's heuristic scheduling would work, right? Let's consider a set of jobs that are waiting in the queue to be scheduled. Now, based on the scheduling policy, let's say SRTF, the next job to be scheduled, that is, in this case, the job with the shortest remaining time, is chosen from the queue. And all the jobs here are attached with a resource demand profile, which indicates its best case CPU and memory requirements as predicted by the optimistic profiling technique. So as long as this job's GPU demands are satisfiable in the cluster, Synergy has to schedule this job in the given round. So it first checks if the job's demand along all the resource dimensions are satisfiable by the cluster, right? If it does, then the job is assigned to the cluster. But if it does not, then we tune the job's CPU and memory demands to GPU proportional share if it's requesting more than proportional share of auxiliary resources. And then we retry this placement again. And now if it fits, well and good. But if it still does not fit, then what we do is we find a set of servers that have underutilized GPUs in them, and also which has enough GPUs to fit this particular job. And we have to find the set of jobs in these servers that have been allocated more than proportional share of auxiliary resources. And we pick these jobs that have the over-allocated auxiliary resources, and we switch these jobs to their GPU proportional shares. And we keep doing this as long as we have freed up enough auxiliary resources for this new job to fit. And at this point, when we retry the placement decision, we will be able to place the current job on the newly freed up server. And this scheduling mechanism continues until there are no more free GPUs or no more waiting jobs in the cluster. So with that, let's move on to the evaluation of Synergy. We evaluated Synergy on both physical cluster as well as a trace-driven simulator for a variety of workload scenarios. We deployed Synergy on an internal cluster of 32 V100 GPUs, and we performed simulation experiments on a cluster of 128 and 512 V100 GPUs. And we use a varied mix of 10 models across 3 different ML tasks. The main questions that our evaluation tries to answer are, can our optimistic profiling technique model the job requirements well? Does Synergy improve the overall cluster metrics? And is it close to the upper bound throughput? How can Synergy perform with various workload compositions? Does it scale well to large clusters? And finally, how does it compare to existing multi-resource big data scheduling policies like the DRF? In the interest of time, I'll only discuss a few of these aspects in this talk today, but the detailed evaluation can be found in the paper. So first, we show that the optimistic profiling technique is able to model the trend in CPU and memory sensitivity closely. So Synergy profiles the model at discrete CPU and memory points for about 50 iterations for the ResNet 18 model on a V100 GPU. And this is indicated by the orange line here. And the green line indicates the job throughput that's empirically measured and averaged over 2 epochs. And as we can see here, Synergy is able to replicate the resource demand curve to within 3% of the empirical runs. And this holds across different models. Second, Synergy improves the overall cluster objectives like the average JCT and makespan. So we first evaluate makespan for the FIFO scheduling policy using the baseline GPU proportional allocation, Synergy, and using the optimal policy on both deployment as well as our simulator. And in both these cases, we used a cluster of about 32 GPUs. So there are 3 main takeaways here. First, the runtime with our simulator is close to the deployment numbers, demonstrating the fidelity of a simulator. Second, the makespan that's obtained with Synergy is close to the upper bound solution. And in all our experiments, Synergy tune was within 10% of the optimal upper bound that was predicted. Finally, Synergy tune improves the makespan by about 1.4 times compared to the baseline GPU proportional allocation. We repeated this exercise using the SRTF scheduling policy on a dynamic job trace, and we report the average job completion time across a set of jobs in steady state. So here, Synergy tune improves the average JCT across jobs by 1.5 times. And it also improved the 99th percentile job completion time by 2x. And this is all by performing disproportionate allocation of auxiliary resources, which in turn significantly speeds up individual jobs. Finally, on a simulated cluster of 128 GPUs, we varied the load in the cluster, which is the number of jobs that's arriving per hour in the cluster, and we plot it against the average job completion time of a set of jobs in steady state. And as we see here, Synergy is able to support a higher load compared to GPU proportional allocation by utilizing the cluster resources more efficiently and speeding up the jobs using workload-aware allocation. So to conclude, we presented Synergy, a resource sensitivity-aware scheduler for DNN training. The main insight behind Synergy is that different jobs in the cluster have different CPU and memory requirements. And we use this observation to take away the unutilized auxiliary resources from one job and give it to another in order to improve cluster-wide performance. And Synergy is open source. With that, I'll conclude and I'll be happy to take any questions. Thank you.